Understanding variation is key to interpret the value stream behavior. Not all variation is the same. We need to distinguish between random variation and special cause due to one or several factors. This we can do with the help of statistical process control. When we want to cook a turkey, there are several factors which will affect the outcome. The raw material, the breeding of turkey, the equipment used, the method, the manpower skills, metrics. All these are possible causes of process variation. Every process has variation. Some causes of variation may be identified and acted upon. We can use two metrics for variation which complement each other: the run chart and the frequency distribution histogram. You can see this article in Polyhedrica blogspot. Scan this QR code to download this Excel file to your PC from OneDrive. Close all Excel sheets before you open this one and enable macros. Open the dice sheet. Press reset and keep on pressing F9 to throw the 4 dice. Try to answer these questions based on your exercise. Does each outcome depend on the previous one? Are there any special trends or indication of process change in the run chart? Is this a stable process? Is there a special cause that explains the maximum and the minimum values? Did you do anything different to obtain them? If we have a target to achieve the maximum possible value, will motivation from management help? Is the frequency distribution close to normal, maximum at the center, declining frequency on both sides, symmetrical? What distribution would result in throwing one single die? Why? Is it possible to predict the outcome of one specific throw? Is it possible to predict the frequency of one specific outcome for a large number of throws? Can two different run charts produce the same histogram? No, each outcome is independent of the previous one. This defies some widely accepted fallacies among gamblers. If a number won last year, it has less chance than other numbers to win this year. After 3 consecutive reds, there is more chance of getting a black. We can't see any significant trends up or down. Therefore, this is a stable process. It continues to behave the same way. It is stable despite its large variation. This is what we would expect since we have not changed the way we throw the dice, so the process will continue to behave this way while we do so. We did nothing different to obtain the high or the low values. The outcomes are purely random. Motivation will only produce frustration of the employee and no improvement in this case. The outcome in this case is purely random and the employee running this process has no way to improve it. Some managers, in a case like this, may get the impression that the variation is a consequence of their own positive or negative employee motivation actions, but we know, in this case, it has nothing to do with it. Yes, the histogram is close to normal. This is a stable process following a normal distribution with average 14 and standard deviation around 3. Throwing 4 dice, there is only one combination that gives a sum of 4, all ones, but there are many combinations that give a sum of 14. The distribution of sums of 4 throws follows a normal distribution in spite of the distribution of single values following a uniform distribution, central limit theorem. If we throw a single die, we will have a uniform distribution. All outcomes have the same probability. It is not possible to predict any one outcome. Yes, in this case of a stable process we can know the frequency of each outcome looking at the histogram above for a large number of throws. Yes, two different run charts can produce the same histogram. The histogram cannot tell us if the process is stable. This can be done with the run chart. Stability doesn't necessarily mean that the process is okay, it just means that the process is neither improving nor getting worse. As we increase the sample size, number of dies, the sum of the outcomes follow a normal distribution. Let's now analyze another process. Open variation.xlsm sheet Alt, press Reset, and keep pressing F9 to run the process. We can clearly notice that this process has a significant upward trend, therefore it isn't a stable process, its average is shifting up. Therefore it is very unlikely that it comes from throwing dice, apart from the values above 24 being impossible with 4 dice. In this case of an unstable process, as shown by the run chart, the histogram is completely misleading if we want to predict the process behavior. The histogram predicts that values below 15 have a certain probability of occurring, but from the run chart we see that this is very unlikely. If the process is not stable, as shown by the run chart, the histogram is useless to predict future behavior. We can conclude that the run chart and the histogram are both necessary and they complement each other. First, we must check that the process is stable with the run chart, and only if it is, can we use the histogram to characterize the process behavior. The question is, how do we know if the process is stable, apart from just our impression? What is a significant trend? The answer is to use an SPC chart, sheet Alt SPC. The green and red dots indicate a significant upward trend, therefore this is not a stable process. If it isn't stable, we can't forecast how the process will behave in the future, and our histogram is obviously useless. This represents the number of defects produced by the different operators for 1 week. Supposing you are the manager, based on these results, decide on the actions you would take. What management actions would you take, based on the previous performance results? Talk to Amparo to remind her of our zero defects commitment with the customer. Congratulate Fernando for his results and, maybe, give him a prize. Ask the process engineer to explain why Mondays produce more defects than Fridays. Tell operators that anyone producing above 8% weekly average defects will be penalized. If you have decided on any of those actions, you are wrong. In fact, they may be counterproductive. This would be an example of overreaction on the part of management due to a lack of understanding of process variation. To see this, just press F9 to simulate another week with this same process. Your opinion on who is best or worst may change. You can see here a control charts of the results with the calculated control limits of 20 and 0. To know if there is a significant difference among the employees or among the days of the week, we do a two-factor ANOVA with Excel data analysis. Rows p.value of 0.19, above 0.05, indicate that there is no significant differences among the operator performances based on this sample size. Columns p-value of 0.37, also above 0.05, means no significant differences in the day of the week performance. Management improvement actions, in this case, should be directed to improve the overall process to reduce the defect rate. The process owner may run a design of experiments, DOE, to optimize the critical process parameters to achieve this. Process control. Open variation.xlsm sheet control and press Reset. You have been made responsible to control a machine to ensure the deviation from target is 0 in every run. You can set the adjustment value, positive or negative, to be applied to the next run. Set the adjustment and press F9 for the next run. Repeat for 25 runs. Process control results analysis. Did you achieve your objectives of controlling the process to obtain zero deviation in every run? Why? What strategy did you follow? What could you have done differently? Can you be held responsible for these results? Why? Let us try to adjust every time with minus the deviation. With our adjustments we made the process much worse, increasing variation, standard deviation of 38. This is clearly overreaction. With no adjustments the standard deviation would have been much lower, 14. We see that the process has random variation, and its average deviation is well centered in 0. This means we cannot improve it with our adjustments. In fact, we will increase the variation and make it worse. In this case the operator has been given an impossible task. Someone is shooting at a target and based on the deviation of the impacts, he adjusts the gun sight after each shot. The result has been an increase of the dispersion of the impacts. Therefore, the adjustments have made the process worse. Adjusting the sight after each shot was not a good idea, so let's fire 5 shots without adjustments to decide if adjustment is required. There is a large dispersion, but it is well centered. This means that adjusting the sight will not improve the results. What I need is to learn how to shoot. In this case we can improve by adjusting the sight. If you drop a live frog in boiling water, it will immediately jump out to save its life. But if you put it in a pot of cold water and heat it slowly enough, the frog will eventually pass out without any reaction. Many companies have fallen into this trap. A big disaster generates a quick and effective response, and the company recovers. A slow degradation of their KPIs such as customer sat or long delays pass undetected until it is too late. Statistical process control will help us detect when a significant change has taken place in a process, and corrective action is required. We will use as an example the process of controlling our own body weight. Download this Excel file from OneDrive onto your PC. You can decide the frequency of your data collection. In this example I have collected it daily. It is important to collect it at the same moment, more or less, each day. You can either have your Excel file in your smartphone or in the cloud, Google Drive or Microsoft's OneDrive. Open sheet weight in the Excel file. To enter the timestamp in column A we will use data validation. In cell X1 we have the formula equals now, which will produce the current timestamp every time the sheet is updated. We have defined data validation for the whole column so by clicking in the arrow in the cell the timestamp from cell X1 will be presented, so just click on the timestamp and it will be entered in the cell. SPC uses some rules, developed by the Western Electric company, to detect symptoms of statistically significant trends. The average of all values X bar is the center line in the graph. Sigma is the standard deviation of all values. The most obvious trend symptom is a value above the upper control limit, upward trend, or a value below the lower control limit, downward trend. We define zone A as the area 2 sigma beyond the center line. 2 out of 3 consecutive values in zone A is an indication of being out of control. Zone B is the area 1 sigma beyond the center line. 4 out of 5 consecutive values in Zone B is a symptom of out of control. 7 consecutive points on the same side of the center line is a trend symptom. In this case upward. 7 consecutive points increasing or decreasing is also a symptom of trend. These are commonly used rules to detect statistically significant trends. Green indicates downward trends and red upward. You can see the description of the symptoms by placing the cursor on top of them. If the weight value is black, it means stability, green means significant weight decrease and red significant weight increase. The numbers on the right indicate which rule or rules have detected the trend. You can see a statistically significant decrease from March to April. You must decide whether a 2 kilo decrease is enough. In sheet weight, meant to be used from a smartphone, there is no graphic, we just show alerts of significant trends. In sheet SPC you can find an SPC chart for individuals you can use as an alternative. The red dots indicate increased trends and the green dots decrease. These are some conclusions. An understanding of process variation is essential to take the right improvement actions. Decisions based on one single outcome can lead to overreaction and making the process worse. A slow trend may pass unnoticed, causing process degradation until it is too late. Statistical process control is required to distinguish between a significant change in the process and intrinsic process variation. The actions required when there is a special cause or just common cause are different. Statistical applications such as Excel data analysis tools can help in further analysis. SPC Western Electric rules can even detect small trends and alert the operator to make corrections before the process gets worse. Manual pencil and paper SPC charts only detect a point beyond the limits but not all the other trend symptoms. See the article Statistical Process Control.